In this video, we're talking about log properties, and these are really important to be able to work really fluently with logs and work with them in the way that we're going to need to be able to as we go along. So I'm going to go through the properties one by one. So we've got log base b of b equals 1, and these should make sense if you think about them for any length of time. This is saying that the exponent that you have to raise b to, the base, to get b would be 1. So this, if we changed it to exponential form, would say that b raised to the 1 equals b. And then similarly here, log base b of 1 equals 0. This is saying that if we take b and raise it to the 0, we get 1. So these all align with what we know about exponents. All right, so one that's a little less obvious, log base b of a product of two things, p times q, is equal to log base b of p plus the log base b of q. Similarly, we've got log base b of p divided by q is equal to log base b of p minus log base b of q. And then log base b of p raised to the n. So this n is inside of the log function, only p is raised to the n, is equal to n times log base b of p. And I know it's weird to see this without any numbers, but we'll start working with numbers once I run through these properties. All right, b raised to the log base b of p is equal to p. And that's because the log base b of p, that we defined as the number that you raise b to in order to get p. And then log base b of b to the x is equal to x. And let's see. Oh, and then I'm going to look at this one in a little more depth and see like why it works, just using property 2. So log base b of p to the 4th, for instance, that is log base b of p times p times p times p. And we can split this up, this product, up into a sum of 4 terms. Log base b of p, log base b of p, plus log base b of p, plus log base b of p, which is equal to 4 log base b of p. So those are the properties. You might want to take a screenshot or write them down now because we'll be using them as we go, and I'll scroll up so we won't really be able to see this as we do examples. So I'm going to write the expression as a single log with coefficient 1. And again, it might seem kind of weird, like why we do this now, but we're really just preparing and setting up and making sure we're really comfortable working with logs for when we need to use this later on for graphing or for limits in calculus or derivatives, that sort of thing. So I want to write this as a single log. So right now these are like a sum and difference of logs, and I want to write it so that we have just one log. And I'll use those properties. So first, I'm going to take these coefficients and put them back in here as exponents using this 4th property here. So I'm doing a first. So I'm moving the coefficients to exponents first. And now they have the same coefficient in front of them. And I also want to point out they have the same base. If these functions don't, or these logs don't have the same base, you cannot use these properties. These require the same base. So now I'm using property 3, which says that the difference of 2 logs, you can combine it into a single log by writing it as a quotient of those inputs. And then that's our answer. So we're trying to write it as one log. We did. It's just a single log with a coefficient of 1, log base 2 of x cubed over y to the 4th. So in this case, I use property 4 and property 3. And property 3, I started with it like this, and then I condensed it to this side. So sometimes I use the left side, sometimes I'll use the right side. So here I have a couple things that have a coefficient that's not 1. So I'm going to have to change that first. So I'm going to move these exponents to be, or excuse me, these coefficients to be exponents. So we've got log base, log, remember log base with no base written there is log base 10 really. So we've got log x squared minus 16 minus log of x plus 4 all to the 3rd, and then plus log of x squared. And now I can use properties 2 and 3 to combine them, and I did it in 2 steps. So I first just combined these two. So the log minus the log, I combine those into a single log. You could do this all in one step if you wanted, but I just wanted to be clear. So I really just used property 3 here. Now I'm going to use property 2. And then at the same time, let's see, I made sure I had parentheses here because this x squared is multiplied by the entire numerator here. And then that's my answer. All right, let's try the other way around. So this time the log is already condensed and we want to expand it. So we want to expand it into sums, differences of constant multiples of logs. So here I have ln, which is, as a reminder, it's log base e. So I'm going to rewrite the square root as an exponent. And if you need fewer steps to do this, it's totally fine. But I just want to be clear as to what I'm doing along the way. Now I'm going to use property 4 to get this exponent down in front as a coefficient. All right, I have a difference of some things. So I have the numerator and denominator here, so I can split that up. Oh, and I factored actually is what I did first. Again, if you do this in fewer steps, totally fine. So I factored this numerator because it can be factored. So I'm using properties 2 and 3 now. So I'm splitting up this one because I have a product. I have x times x plus 1, so that's why I have a plus between these logs now. And because I'm dividing by an x minus 3 inside the log, I can subtract this 1/2 ln of x minus 3. I want to point out, though, that every term here has the 1/2, and that's because everything was under this square root. So everything was raised to the 1/2 power. So make sure you distribute that 1/2 or keep it with every single term, either way. The other option is that you could leave it in parentheses and have the 1/2 out in front of everything. So that's another option. So 1/2 times all of ln of x plus ln of x plus 1 minus ln of x minus 3. That is another totally fine answer. Oh, now up here again. Sorry. So this time, because I have a different exponent on the numerator and the denominator, I'm going to separate the numerator and denominator first into 2 different terms. I didn't do that first here because they both had the same, both the numerator and denominator had the same exponent. We could have done it this way, and we thought of it as the numerator having a square root and the denominator having a square root. That would also work. But in this case, I don't have a choice. I have to split it up. So this is going to become log base b of the cube root of y minus log base b of b to the 5th. Then I can use a different property on each of those terms. So the first term, I'm going to rewrite the cube root as an exponent. And again, if you want to do this in fewer steps, you're welcome to. And then this second term, I can use property 6 to just get a single number. So I've got log base b of y to the 1/3 minus 5. This log base b of b raised to some number, it's always going to equal this number. So it just simplifies to a minus 5. I added in parentheses just so I was clear about the fact that this minus 5 is not inside of the log. It is log of only the y to the 1/3, and then the minus 5 is separate. And now I can use property 4 to bring this exponent out in front of the log. And so I finally have 1/3 log base b of y minus 5. And you might want to rewrite it so that you have the minus 5 in front, just so you don't accidentally try to put the minus 5 inside of the log, because it does make a difference. But both are correct. All right, one more example here before we do another formula. So find the x-intercept of y equals 3 to the 1 minus x minus 4. Remember, just to find x-intercepts, we let y equals 0 and solve for x. So I'm going to have 0 equals 3 to the 1 minus x minus 4. Move the 4 over, and then I'm going to take the log of both sides, and that allows us to bring down this exponent in front. And because it's problematic that the x is in the exponent, I can't really solve for it. So to counter that, I'm going to use the log. And it really doesn't matter what log you choose. We often just choose natural log just for some consistency, but you could choose log base 3 because you know that that will cancel this, but it really doesn't matter. They're all going to be equivalent. All right, so I'm going to use ln. So I have to do that to both sides of the equation, much like you would add a number to both sides of the equation or divide by a number on both sides of the equation. We have to take the natural log or whatever log you choose on both sides of the equation. And remember, natural log, it's like a square root. So it's natural log of something. So you have to put the ln in front because you're taking the ln, or natural log, of this 3 to the 1 minus x. And you're taking ln of 4. So it's not 4 and then the ln. That doesn't make any sense mathematically. That notation doesn't have any meaning. All right. So then I'm using property 4 to bring this exponent down in front. So I've got ln of 4 is equal to 1 minus x times ln of 3. And just be careful that you include parentheses around this 1 minus x, because the ln of 3 is multiplied by the 1 and by the negative x. So I'm distributing this ln of 3. Ln of 3 times 1 is just ln of 3. And then ln of 3 times x is where I'm getting this x ln of 3. And it's weird, but ln of 3 and ln of 4 are both numbers. So we can treat them like they were 5 or 7 or whatever. All right, so now I'm going to try to get x by itself. So I subtracted ln of 3 from both sides. So I've got ln of 4 minus ln of 3 is equal to negative x ln 3. And you could combine these if you wanted to at this point. I'll wait until the end, or we even don't have to. And then I'm trying to get x by itself, but x is being multiplied by the number ln 3 and negative 1. So I'm going to divide by negative ln of 3 on both sides. And I finally get x is equal to ln of 4 minus ln of 3 over negative ln of 3. We cannot cancel these because of the difference or sum. A sum would also mean that we couldn't cancel in the numerator here. So we cannot cancel those, and that's our final answer. And like I said, you could combine these two using property 3 and get ln of 4/3 over ln of 3. And again, you still cannot cancel these natural logs. Those are functions, okay? So you cannot cancel those. Those have to be there. Last thing, we've got a change of base formula. So if we have a log base b, but we want to change it to a different base, we can. So if we have log base a of x, that is equal to log base b of x, the desired base that you want to change to, over log base b of a. So you're really taking this, goes to the numerator, this base goes to the denominator, and then you have your new base here. So for example, let's change log base 5 of 7 to a base 3 log. So we want to identify like what each piece is. So this 5 in our formula, that's the a, that's the base of the original log. Then the 7, that's the x in this formula. And then last, this 3, that's b equals 3. That's the base we want to change it to. So now that I've identified a and b and x, if we're using this formula, we can plug it directly into the formula. So we have log base 5 of 7 is going to equal log base 3 of 7 over log base 3 of 5. And that's our answer. So these properties of logs are really important, and it's really easy to get them a little mixed up. So I would recommend writing them down and using that sheet that you write them down on as you go through problems, whether it's the homework or practice problems or whatever. It's really, really helpful to have those handy.